Good afternoon. We are going to start with lecture number 23 of electric drives course. In the last few classes, in fact, we had been looking at converter fed DC motor drive. So we looked at, first of all, single phase, fully controlled converter fed, separately excited DC motor drive. Then we had looked at single phase, semi-controlled converter fed, separately excited DC motor drive. And after that, we had looked at three-phase full converter fed, separately excited DC motor drive. And we also looked at three-phase semi-controlled converter fed, separately excited DC motor drive. And we looked at actually as a special case, three-phase full converter with the freewheeling diode. And we also took a look at the comparison between the semi-converter and a full converter with freewheeling diode, and which one is better for obtaining continuous conduction and so on. And finally, we also looked at series motor drive. So if I feed a DC series motor with any of the converter, in that case, how does it behave? How is it different from separately excited DC motor drive? So we looked at that as well. And one thing specifically we said was, if we want only one quadrant of operation, we can go for diode converter, or even variable voltage if we want, then we can go with semi-controlled configuration. Whereas if we want two quadrants of operation, then we will go with full converter. On the other hand, if we wanted four quadrants of operation, that is forward motoring, forward regeneration, reverse motoring and reverse regeneration, we will require something called dual converter. And we looked at dual converter also in the last class. So what we said was, if two converters, fully controlled converters, are connected back to back, in that case, in anti-parallel configuration, then this will be generally called as dual converter. So it can have all four quadrants of operation possible. This is what we said in the last class. In today's class, we'll try to work out a few numerical examples for three-phase converter fed DC motor drive as well as dual converter. Then we will also take a look at series motor drive one problem. So let me start with a problem on three-phase full converter fed separately excited DC motor. So we are going to start with this. Okay, so the problem statement is somewhat like this. A 230 volts, 650 RPM, 100 ampere, separately excited DC motor has an armature resistance of 0.478 ohm. Please note, this is a very high resistance. I don't know why such a large value of resistance has been given. because IARA will come out to be 47.8 volts, which is way too high. But this is the statement that is being given. So I'm just taking this at face value. That's it. So armature resistance is 0.478 ohm. A three-phase full converter with a line voltage of 230 volts, 50 hertz is controlling this motor. Okay, so the line voltage RMS value is given as 230 volts. Now, what is being asked is calculate the speed phase current RMS value, fundamental source current value, per phase, of course, because if we are talking about AC side current, it has to be per phase. At alpha equal to 60 degree and alpha equal to 120 degree. Assuming that the load torque is 300 Newton meter and the armature current is ripple free. Calculate DPF, displacement power factor, and PF, power factor. So let us try to work out the solution for this problem. First of all, let us try to calculate what is the rated value of back EMF and back EMF constant. I think these two are extremely important. So we can say at rated condition, back EMF is going to be equal to VA minus IARA. So I can calculate EB equal to 230 minus 0.478 multiplied by 100. So this is back EMF, and this back EMF is 230 minus 47.8 volts. So it will come out to be 182.2 volts. And if I calculate what is 650 RPM when converted into radians per second, that works out to be 68.07 radians per second. Now we should be able to calculate what is the back EMF constant at a given excitation or rated excitation. K phi is going to be EB divided by omega m. So 182.2 divided by 68.07. This is going to be our back EMF constant, which comes out to be 2.677 volt second per radian. So this is the back EMF constant. Okay. Now let us try to calculate what happens at alpha equal to 60 degree. So at alpha equal to 60 degree, first of all, let us try to calculate what is VA average value on the DC side of the fully controlled converter. We wrote this expression earlier also, which is 3Vm divided by pi cos alpha. So this is going to be 3 multiplied by 230 multiplied by root 2, because this Vm is going to be line voltage peak. So this is going to be line voltage peak value. Okay. So this line voltage peak value is 230 multiplied by root 2. So this divided by pi and cos of 60. This is going to be the value of average armature voltage at alpha equal to 60. And this comes out to be at alpha equal to 60. This comes out to be 155 volts. This comes out to be 155 volts. So now what we need to do is, if torque is equal to 300 Newton meter, I can calculate IA equal to torque divided by K5 for a separately excited DC motor drive. So I should be able to calculate this as 300 divided by 0.677. This is going to be the current that has to be drawn by the motor at rated excitation to develop a torque of 300 Newton meter. And this comes out to be 112 ampere. So this comes out to be 112 amperes. So if this is 112 ampere, we should be able to calculate back EMF at 300 Newton meter torque and at alpha equal to 60 degrees. So how much is the back EMF? If we try to calculate, this should be VA minus IARA, and VA happens to be 155 volts at alpha equal to 60. So 155 minus 112 multiplied by 0.478, which is the armature resistance. So this particular voltage comes out to be 155 minus 112 multiplied by 0.478, and this has to be divided by K5. So if I call this as EB dash, I should say omega M nu or omega M dash will be EB dash divided by K5. So this is 155 minus 112 multiplied by 0.478 divided by 2.677. And this comes out to be 37.9 radians per second. Or indirectly, I can say, if I just convert that into RPM, this comes out to be 361.8 RPM. So this is the speed at this particular value of firing angle, that is alpha equal to 60 degrees, and at a torque of 300 Newton meter. Under 300 Newton meter condition, it is drawing a current of 112 ampere, which is slightly higher than rated current. Okay. Now, we had already said that supply side per phase RMS current, that will be root of 2 by 3 times I armature current. And we are assuming the armature current to be ripple free. There is no ripple at all in the armature current. So if I am trying to look at the DC voltage, the DC voltage will be somewhat like this. This is how the DC voltage will be at alpha equal to 60 degrees. And if I assume that the back EMF value is somewhat like this. So this is going to be EB, whereas this is going to be the armature voltage, in which case we are going to have actually the current increasing and decreasing and so on, but we are going to neglect any variation in the armature current. We are going to assume that it is ripple free. So this green color waveform is armature current. Okay. But we are going to assume it to be ripple free. That is the reason why, if I assume that initially 6 and 1 are conducting, then 1 and 2 are conducting, this is 2 and 3, then this is 3 and 4 and so on. We are going to have the source side current somewhat like this. I'm going to have the current starting like this, and it is going to go on for 120 degrees. Then it is going to keep quiet for 60 degrees. Then again, it is going to go on for 120 degrees. So this is 1 conducting along with 6, and this is 1 conducting along with 2. Here 2 and 3 are conducting. Here 4 and 3 will be conducting. Here 4 and 5 will be conducting. So this is the supply side current, what you see on A phase. So for this, we derived the RMS current to be root of 2 by 3 times armature current. So this will be 112 multiplied by square root of 2 by 3. This is going to be the armature current. I mean, this is going to be the RMS per phase current on the supply side. And this comes out to be 91.5 ampere. So if I want power factor, I should calculate this as the real power delivered to the DC motor divided by the apparent power taken in from the supply side. So real power, I should be able to calculate this as whatever is VA average multiplied by IA. That has to be divided by root 3 VL RMS I RMS per phase. So this will come out to be the DC side voltage, the average voltage we calculated as 155, and IA is 112 ampere, and root 3 times 230 volts is the line voltage RMS value, and per phase current RMS value is 91.5. So this will be the power factor what we can calculate. And this power factor comes out to be 0.47655. Please verify this, but this is what is coming out to be the power factor. But if you may recall, we talked about displacement power factor also. So the displacement power factor is cos of alpha itself for a fully controlled converter. So that is cos 60, which is actually 0.5. So this happens to be the displacement power factor. Another thing that is being asked is, what is the fundamental source current value per phase? So fundamental source current value, if you may recall, again, we drew the waveform just now for the A phase current. So it will conduct for 120 degrees. It will be keeping quiet for 60 degrees. Again, it will conduct for 120 degrees. So if I plot the current, so if I may say that for initial 30 degrees, maybe it is not going to conduct at all. So it is going to conduct from 30 to 90 along with 1. So 6 and 1 will conduct for 60 degrees. Then 1 and 2 will conduct for 60 degrees. So if I may call this portion as pi by 6 or 30 degrees, this will be 5 pi by 6. And this entire duration will correspond to 120 degrees. And again, it will keep quiet for 60 degrees. So it is going to keep quiet for 60 degrees. There will not be any current at all. Then the current will go into the negative direction and it will go on like this. So this is going to be 2 and 3, which are conducting at this juncture. Then this is going to be 3 and 4, and this is going to be 4 and 5, and this is going to be again 120 degrees. And it will keep quiet for another 30 degrees before the cycle ends. So, according to Fourier expansion, if we are writing a non-sinusoidal periodic waveform as sigma, that is f of omega t, can be written as f naught, which is actually the DC value, plus sigma n equal to 1 to infinity an cos n omega t plus bn sin n omega t. So this is what Fourier expansion says, in which f naught is f of omega t d omega t, which is averaged over integrated and averaged over 0 to 2 pi. So this is going to be the average value. And if I'm talking about an is going to be f of omega t cos n omega t d omega t. This will be integrated. Let us say from 0 to pi, if I integrate it, I will have to say 2 by pi integral of 0 to pi f of omega t cos n omega t d omega t. This will be an, and bn will be 2 divided by pi 0 to pi f of omega t sin n omega t d omega t. Okay. So let us try to get fundamental component of A phase source current. Okay, so this is IA phase. Whatever we have written here is A phase source current. So let us try to get the fundamental component of A phase source current. So let's use these two expressions. So I should say A1 equal to 2 divided by pi. From 0 to 30 degrees, there is no current at all. So I have to integrate this from pi by 6 to 5 pi by 6. And if I may call this amplitude as IA, so I should say IA multiplied by cos omega t d omega t. This is going to be the peak value of fundamental component of current, which is cosinusoidal component. So this can be written as 2IA divided by pi. For cos, if I try to write the integration, that will be sine. So I should say sine of pi by 6 minus sine of 5 pi by 6 minus pi by 6. Okay, so this is going to be sine pi by 6 minus sine pi by 6. So this will work out to be 0 because sine of 5 pi by 6 is same as sine pi by 6. So this will work out to be 0. So this will not exist. This will be 0. A1 will be 0. Now if I try to calculate B1, this will be 2 divided by pi. Again integrated from pi by 6 to 5 pi by 6. I have to integrate IA sine omega t d omega t. So this will work out to be 2IA divided by pi. And for sine, the integral is minus cosine. So I'm going to have cos of pi by 6 minus cos of 5 pi by 6. So cos of pi by 6 is root 3 by 2 and cos of 5 pi by 6 is minus root 3 by 2. So we are going to get 2 root 3 IA divided by pi. So this is the peak value of fundamental current. So if I try to draw the fundamental current, I am going to have something like this as the fundamental current. I am not drawing this to scale. So this is going to be the kind of fundamental current we are going to see. So this is the fundamental. So the peak of this value happens to be 2 root 3 divided by pi. So RMS value of sinusoidal fundamental current is going to be equal to peak divided by root 2. And peak happens to be 2 root 3 IA divided by pi. And this has to be divided by root 2. So root 2 multiplied by root 3, that is going to be root 6 by divided by pi IA. This is going to be the RMS value of fundamental current. So I should be able to calculate what is the RMS fundamental current in this particular case. So RMS fundamental current is going to be 112 amperes is the basic fundamental, that is the average value of armature current multiplied by root 6 divided by pi. So this is going to be the RMS value of fundamental current. Okay. So this comes out to be 87.4 ampere. So this comes out to be 87.4 ampere. Now, what else is being asked? Another thing that is being asked is for alpha equal to 120. They are asking us to calculate all these speed, phase current, RMS value, fundamental source current value, and so on for a torque of, again, the same 300 Newton meter. So let's try to calculate for alpha equal to 120 degrees. So the first thing we need to do is to calculate what is 3 Vm divided by pi cos alpha. This is going to be the average armature voltage. So this will come out to be 3 Vm divided by pi cos of 120, which is actually the reverse of or negative value of cos of 60. So this will come out to be minus 155 volts. So what you have to remember is this is our fully controlled converter. And I'm connecting the DC motor drive here. And alpha is greater than 90. So I'm going to get plus here and minus here. And back EMF also we should have reversed like this. So this will be EB and this will be VA. And if I am talking about regeneration at this point in time, then from EB, the current is going to go towards VA. So EB has to be greater than VA for regeneration to occur. If I want regeneration to occur, then EB should be greater than VA. So in which case I should write VA minus IARA. VA plus IARA should be equal to EB. This should be the case for regeneration. So my 155 volts is the voltage, average voltage across the armature, but with the reverse sign. IA will be still 112 ampere for PE equal to 300 Newton meter. If the torque is 300 Newton meter, I'm going to have IA to be 112 ampere. So this will be 112 multiplied by 0.478. So the total value of this will uh, give what is back EMF. So that comes out to be 208.74 volts. So if this is the voltage, then we should be able to calculate the speed. The speed will be equal to 208.74 divided by K5. And K5 we already calculated. So the K5 value, what we calculated was 2.677. So we should be able to calculate this as 208.74 divided by 2.677. So this will be the speed. And this speed comes out to be 77.98 radians per second, or this also can be expressed in RPM as 745 RPM approximately. So this is going to be the speed. Now I can calculate again IRMS, which is same as the previous case, or same as the case corresponding to alpha equal to 60 degrees. And the same way I fundamental also, it will be same as the case corresponding to alpha equal to 60 degrees. Only thing is the real power fed back. This is not being drawn, it is fed back to the supply. Thus, that will be corresponding to 155 multiplied by 112. But this should actually have a negative sign if we are talking about what is the power drawn from the supply. Rather, the power is fed back to the supply. So that is why if you try to calculate what is the displacement power factor, that will come out to be negative because the power is not being drawn. It is rather being supplied back. So this will be cos 120 degrees. That's why we get a negative value because the power is not drawn from the three-phase supply. It is rather being supplied back to, the power is fed back to the three-phase supply. Okay. So this corresponds to the single phase, three-phase full converter operation in motoring zone as well as regenerative braking zone. So let us try to do another numerical example. So this numerical example on three-phase semi-converter. So let us use the same problem what we had already looked at for three-phase full converter case. So the same three-phase, same separately excited DC motor is being fed by semi-converter with 230 volts 50 hertz supply. And from here, let us try to calculate what is RMS current and so on and so forth. So let us try to do this. So again, the DC motor is a 230 volts, 100 ampere, 650 RPM DC motor with RA being 0.478 ohm. That's what is being given. Okay. So first of all, we should remember that three-phase semi-converter average output voltage on the DC side will be 3 Vm divided by 2 pi multiplied by 1 plus cos alpha. This is what is the three-phase semi-converter's output voltage expression. So let us first of all do it for alpha equal to 60 degree and TE equal to 300 Newton meter. So what happens in this particular case? So let us first of all calculate what is VA, that is V3 multiplied by root 2 multiplied by 230 divided by 2 pi. This is being multiplied by 1 plus cos 60. So this is 1.5 times 155 volts. Okay. So that comes out to be 232.764 volts. So this is the voltage output of the semi-converter. Now VA minus IARA is going to give us EB, which is the back EMF. So in this particular case, it should be 232.764 minus the armature current is still going to be 112 ampere. That is not going to change. So I can write 112 multiplied by 0.478. So this is going to be the back EMF. Now, if I want what is omega m speed, now I have to divide EB by K phi. And K phi, we calculated that to be 2.677 volt second per radian. So I have to substitute the same value here. And I can calculate this as the speed. And the speed comes out to be 66.94 radians per second, which is incidentally 639 RPM. So in semi-controlled converter case, we are getting 639 RPM, whereas in the case of fully controlled converter, when we looked at an alpha of 60 degrees, we were having the speed to be, how much was the speed? So the speed came out to be 361 RPM, 362 RPM at the most, whereas we are getting 639 RPM in this particular case. So semi-converter always gives a higher speed for the same firing angle and for the same torque value, which we already talked about when we drew the torque speed characteristics last time, right? We compared the torque speed characteristics of the full converter with that of a semi-converter. So this is what had happened. Now let us try to calculate what is IRMS value. IRMS value, if we want to calculate, the first thing that we need to do is to draw the waveform corresponding to three-phase semi-converter at alpha equal to 60 degrees. So this is single phase voltage. This is the second phase voltage. And this will be the third phase voltage. So this is VA, this is VB, and this is VC. And this is alpha equal to 0 degree point. This will be 30 degree. So this is going to be alpha equal to 60 degrees. So we are going to fire 1 here and 2 is fired. So this is 30. So 2 will be fired. 3 will be fired at this point. And we are going to have 5 fired at this point. So we will have, this is 6 conducting interval, and this is going to be 2 conducting interval, whereas this is 4 conducting interval. So we are going to have 1 and 2 conducting until this point. So I will have from here, from this point until this point, for 120 degrees, I'm going to have 1 conducting continuously. So I'm going to have from here until here, this is going to be IA phase current. And 4 is going to start right away immediately and 4 will continue until here. So this is going to be conduction of 4. So this is 1 and this is going to be conduction of 4. So again, this duration is 120 degrees and this duration is also 120 degrees. So basically it is going to conduct for 240 degrees out of 360 degrees. Okay. And it has to be multiplied by the current value, which is actually the armature current itself, which is going to be IA. So square root of this will give me what is the RMS current per phase. And this will come out to be again root of 2 by 3 times ID. This is ID or DC link current or armature current. That is going to be the RMS value. So we should be able to calculate the RMS the same way. So I should say 112 multiplied by root of 2 by 3. So this came out earlier also as 91.5 ampere. So if I try to calculate what is the power factor is going to be VA average value, IA average value divided by root 3 times VRMS and IRMS. Okay. So VA in this particular cases, we calculated this to 32.764 volts. So this is going to be 232.764 multiplied by 112 ampere. This has to be divided by root 3 times 230 times IRMS, which is 91.5 ampere. So the power factor in this particular case comes out to be 0.716. So please note that the power factor in this particular case is 0.716. It is delivering a higher amount of power because the voltage is higher. For the same kind of apparent power drawn from the supply. Whereas what we got as the power factor in this particular case is only 0.47655 for the fully controlled converter. So the fully controlled converter definitely had a lower power factor as compared to the semi-controlled converter. Okay. One more thing that we need to do is for the case of alpha equal to 120 degrees. So when alpha is 120 and TE is 300 Newton meter, we have to calculate what is the speed. So in this particular case, if TE is 300 Newton meter, IA is still 112 ampere. So we will have to calculate 3 Vm divided by 2 pi multiplied by 1 plus cos alpha. That is going to be what is the armature voltage, applied voltage. So cos alpha will be cos 120, which is minus 0.5. So we are going to have 0.5 multiplied by 3 Vm divided by 2 pi. And this comes out to be 155 divided by 2. That is the voltage that we are going to have in this particular case. So that is 77.6 volts approximately. So if this is 77.6 volts, now how do we calculate the value of speed? The speed is VA minus IARA. That is going to be equal to EB. And we are going to say EB divided by K phi is speed. So we should write 77.6 minus 112 multiplied by 0.478 divided by K phi. This is going to be the speed. So in this particular case, the speed comes out to be 85.67 RPM, or in radians per second, it is 8.971 radians per second. That's it. Okay. Now, how do we calculate the RMS current? So for that, let me draw the waveform once again. If I don't draw the waveform, especially in semi-controlled converter case, it could be completely erroneous. We cannot assume root of 2 by 3 times armature current is going to be the actual RMS current. That is not really done in the case of semi-converter. You have to draw the waveform. Unless you draw the waveform, you will not be able to infer what is the armature current. So this is VA, this is VB, and this is VC. So this is going to be VC. Okay. Now alpha is 120 degrees. So this is where alpha is 0. So from here, this is 30. This is 60. So 90. 90 plus 30, this is 120. So this is where we are going to fire 1. And again, we are going to fire 3 at this point and 5 at this point. So these are going to be the firing points for the 3 controllable devices in the semi-controlled converter. I hope you recall the circuit of the semi-controlled converter. So this is the semi-controlled converter. We call this as T1, this is T3, and this is going to be T5, whereas the other 3 are going to be diodes. These are going to be diodes. Okay, and here is the DC motor drive, which is connected here. Now, this is A phase, this is B phase, and this is going to be C phase, where they are connected together. Now, this is going to be D4, this is going to be D6, and this is going to be D2. So we will have here, this is B phase negative side. So this is going to be device number 6 conducting. This is going to be device number 2 conducting. And this is going to be device number 4 conducting. So if you look at it, only from this point until this point where 4 is not yet taken over. So this is where I'm going to have A phase current manifesting itself. So this is going to be I1, device number 1. And device number 4 might conduct here, but because 1 and 4 are simultaneously conducting together, this is the way the current is going to flow. So from here till here, for this 60 degrees, I'm going to have 1 and 4 conducting. So this is going to be freewheeling. So there will not be any A phase current. Now from here, 3 and 4 will conduct. So from here until this point, I'm going to have I4 showing up on the A phase side. So this is going to be IA. Whatever I have drawn in blue, this is going to be IA. So this is only 60 degree duration. This is also only 60 degree duration. So in this particular case, if I try to look at it, IRMS A phase will correspond to only 60 degree duration. So IA multiplied by 60 degree duration, but I have to say this as maybe 0 degree to 60 degree, whereas it has to be averaged over the entire half cycle, because 60 degree duration it conducts for the positive half cycle, 60 degree duration it conducts for the negative half cycle. So this will come out to be pi by 3 divided by pi, and I should say IA square d omega t, and I have to take the square root of this. So this is going to be 1 by 3 or IA divided by root 3. This is going to be the RMS value for alpha equal to 120 degrees case in the semi-controlled converter. So this RMS current comes out to be IA divided by root 3. So this RMS current will be lower. So IRMS for alpha equal to 120 and semi-controlled converter case will be less than IRMS for alpha equal to 60 semi-converter case. And also it will be less than IRMS for alpha equal to 120 for full converter case. Because there also it will conduct for 120 degrees in the positive half cycle and 120 degrees in the negative half cycle. So IRMS value is smaller, because of which we are going to have, if I calculate the power factor in this particular case, power factor is going to be real power divided by apparent power. So real power in this particular case will be, if I talk about VA multiplied by IA divided by root 3 VRMS multiplied by IRMS. So here I'm going to write this as VA, which was about 77 volts or something. What we calculated was 77.6 volts. So this is 77.6 multiplied by 112. And this is going to be root 3, 230 volts multiplied by 112 divided by root 3. That is what is RMS value. So this root 3 and this root 3 will get cancelled. This 112 and this 112 will get cancelled. So we are getting the power factor in this particular case. If at all we calculate as real power divided by apparent power, this will be 77.6 divided by 230. This is going to be the power factor, what we get in this particular case. But it will be very difficult to calculate the fundamental current and displacement power factor, because these two currents, I1 and I4, are not symmetrically distributed over the entire cycle. So let's not bother ourselves with calculating the fundamental component of current and displacement power factor for this three-phase semi-controlled converter case, because the semi-controlled converter really behaves in a very special manner as compared to the fully controlled converter. There is no symmetry at all. Let's try to do one problem on dual converter. So the statement is somewhat like this. The problem statement: a three-phase dual converter is used to control a 100 HP, 600 volts, 1800 RPM separately excited DC motor. Supply voltages three-phase 480 volts, 60 hertz. Armature resistance of the DC motor is 1 ohm. And inductance, armature inductance is 5 millihenry and back EMF constant is equal to zero point 0.3 volts per RPM. Please note this. It is volts per RPM. Rated armature current is 130 ampere. So for this kind of a current value, even this resistance is way too high. I don't know why it is so high anyway. Now, assuming ripple-free IA rated being drawn by the motor, calculate speed and power input to the machine at alpha equal to 60 degrees and at alpha equal to 120 degree during regeneration. So when we do the solution for this problem, the first thing that we can notice is 100 HP means 100 multiplied by 750 watts. So this will be 75 kilowatt machine. This will be a 75 kilowatt machine. So let's first of all calculate at alpha equal to 60 degrees. We are going to have VA equal to 3 Vm divided by pi cos alpha, which will be 3 multiplied by 480 times root 2 divided by pi cos of 60 degrees. So this comes out to be 324 volts. So this is the voltage that is coming up at alpha equal to 60 degree. Now speed in RPM is going to be EB divided by K5 because K5 is given in volts per RPM. So EB is going to be 324 minus 130 multiplied by 1 divided by K5, which is 0.3. So this comes out to be 646.7 RPM. So this comes out to be the speed. So the speed is 646 RPM. So under this condition, power input to the machine is going to be VA multiplied by IA average value, which is 324 multiplied by 130. So this is going to be the power, so which is actually 42.12 kilowatt. We can also calculate it a little differently if you feel like it. You can calculate root 3 VL IL cos phi. And we should assume cos phi is same as displacement power factor, which is an approximation. So we should write root 3 multiplied by VL, which is 480 volts, right? Because line voltage RMS is given to be 480 volts and IL is the per phase RMS current, which will be 130 multiplied by root of 2 by 3. So that will be the RMS current and cos phi will be same as cos 60. So this is going to be the overall power input. This is a little higher than what we calculate here. So this is coming out to be 44.12 kilowatt. That is probably because the displacement power factor generally comes out to be larger than whatever is the actual power factor. The actual power factor will be smaller because there are harmonic contents in the current. That is the reason why it is going to be smaller. So this happens to be our power input. If we look at what happens at alpha equal to 120 degrees. At alpha equal to 120, we are going to have VA equal to 3 Vm divided by pi cos alpha. Cos 60 is same as cos 120, only with a negative sign. So this is going to be minus 324 volts. So it is exactly similar to what we did in the last problem. So in this particular case, we are going to say this is regeneration, and regeneration occurs only when EB magnitude is greater than VA. So we have to write VA plus IARA is going to be EB, and this EB divided by K5 is going to be the speed. So in this particular case, we should be able to write this as 324 plus 130 multiplied by 1. That is going to be the total voltage, which is actually coming out to be 454 volts. So this will be 454 divided by 0.3 volts per RPM. So the RPM in this particular case comes out to be 1513.33 RPM. And in this particular case, power fed back to the three-phase supply. That will be minus 324. So I should not write minus because power is fed back. That is the reason we are taking a minus sign here. So 324 multiplied by 130, which is actually 42.12 kilowatt of power is being fed back to the three-phase supply. So that is the reason why we get this as negative power. Okay. So if you actually look at the waveform for the dual converter in the three-phase case, so VD1 is the DC voltage corresponding to alpha equal to 60 for the converter 1. So if you may recall, we had written earlier the complete circuit diagram for the dual converter. So let me try to draw that once again. So what we are going to have is on one side, we are going to have the three-phase full converter like this. And we are going to have the three-phase full converter on the other side in anti-parallel condition like this. And we are going to have a reactor which is connecting these two converters just to make sure that the instantaneous voltage differences do not trigger a huge current, and this is the DC motor drive. And this is the three-phase supply. And the three-phase supply, what is connected to this particular converter is also going to be common between the two converters. The three-phase supply is common between the two converters. So this is the second phase, and this is going to be the third phase. This is the third phase. So this is how the connection is done for the dual converter. So this is the second phase, and this is the third phase. So these are the three-phase power supply lines, and this is A, this is B, this is C. And this is working at alpha equal to 60 degrees, whereas this is going to work at alpha equal to 120 degrees. And I may call this as VD1, and I'm going to call this as VD2. Please look at the arrow, the way I have written. So this is plus and this is minus. And if I say this is plus and this is minus, this is VD2. So now I'm going to show you the waveform. So this is VD1, which is corresponding to alpha equal to 60 degrees. And this is VD2, which is exactly the opposite of the kind of voltage that we are getting. So this is looking up like this, whereas this is coming down like this. And this is the kind of motor current that we are going to look at. The current which is flowing into the motor, this is going to take the current through this. So this is the kind of current that is flowing into the motor. And part of the current will allow the circulation of the power between converter 1 and converter 2. So this is converter 1 and this is going to be converter 2. So you are going to have the current flowing like this. And this is actually the difference between VD1 and VD2. We are showing this as VD1 plus VD2 because we have shown VD2 in the opposite sense. So if you may recall, this is how we have shown VD2. So the voltage between these two, if this is plus and this is minus, that is VD1 plus VD2 together. That's what we are trying to look at. What is the total value of VD1 and VD2 together? So this is VD1 plus VD2. So this is the voltage across the reactance. And this is what is the A phase current that it is showing. So there will be some amount of circulating current and there will be directly whatever is the armature current. Both of them put together, this is going to be the kind of current we see on the supply side. Okay. We will look at the series motor drive problem in the next class. Okay.